all about frontier energy technologies. And lucky for us, we will be guided by our very own moderator, Hayley Eustace, if I've pronounced that hopefully correctly. She is the angel investor and founder at what I've read to be the first communication and design firm solely focused on deep tech technologies within Europe. And that is quite something, and I think a rare find. So kudos on doing that. Ladies and gentlemen, please welcome our moderator, Hayley Eustace.
Hello, everyone. Hello. I'm so excited about this. I think fusion is really an exciting technology and will really be incredibly consequential for the future. So when I was looking at this, I haven't worked with fusion technologies before. So when I was looking at the space, I thought, what other industries will it affect? It's not just about energy, it's about unlocking so much of the rest of the economy. So I think today, think not just about what if we have fusion technology, but what will happen, what will unlock once we have abundant, clean, safe, almost unlimited energy. It's a really incredible, exciting field. And I think another question I had was why now? The joke is kind of that it's always 30 years away, but that's not actually the case anymore. And so I think today, let's really focus on, what are the breakthroughs that have happened recently and what's coming up very soon. So just a few numbers for you. We've had fusion R&D for the past 70 years, but since 1990 to 2021, 1.8 billion has been invested. From 2021 to now, 15 billion has been invested, so it's an incredible acceleration. And there's even a new VC firm that's only dedicated to fusion technologies in Europe now called StarMaker One. So I think that's quite exciting. And then there was also a recent breakthrough by Commonwealth Technologies in the US that was a high HTS magnet. I will let the experts talk about those. But it meant that the factory was actually 65 times smaller, so it really makes it viable. So yeah, I want to welcome our first speaker, Dr. Maximilian Fleischer. He is the Chief Technical Expert of Siemens Energy. He is on the board of Max Planck, Fraunhofer, and Helmholtz Institutes, and many European commissions. He has been published about 360 times and is the co-inventor in 180 international patents. So please welcome Max.
Can you hear me? If not, I will speak up. Thanks. Thanks for inviting me. Fusion is a nice topic, talking to people. Yes, it's a new source of energy. Will come in 30 years, and my talk is why we do not believe it will be 30 years. It's A, why we believe that the energy system needs a fusion way earlier, and B, what is currently happening with this fantastic startups, which is completely changing the world in fusion now. Disruptions of the energy system. After fire, steam engines, combustion engines, turbines, the last disruption we have seen definitely is renewable energies, wind and PV, scaled to the size of the energy system, also scaled to the costs of the energy system. We started in 2005 with 50 cents per kilowatt hour feed-in tariff, which is factor of 10 too high. Now PV is industrialized, is driven by business models, and you can see here is in most areas of the world the cheapest way to get energy here compared to fossil energy generation. However, what we also observe in our world, it's the volatility of renewables, which tend to render pure renewable-based energy system to become unstable. This is an example of Germany, Saturday, Sunday. It's a generation pattern you see, and here the energy costs. In Saturday, Sunday, we had a in-feed of 80% of renewables into our energy system, which is good with the carbon dioxide, with a carbon dioxide emission, but which is absolutely not adapted to the energy need. We need controllable, we say, dispatchable energy sources. So the offer does not follow the demand, and the result is heavily changing energy prices, which are not good for us at home and even worse for industry. So this is one thing, limits of in-feed of renewables. And the other, especially we need to look on here in Central Europe, is also something geopolitical. Here you see color-coded. In purple you have very good renewable conditions. And these in red you see the industrial load centers. And for example, in west of US or in the east of China, you have a very good fit of industrial load centers and the available of cheap renewables. It's the opposite in Japan, and it's the opposite in Central Europe. So really, it's really a political topic. The energy-hungry industry has to move to areas where energy is cheap. And we cannot offer this in Central Europe. A lot of energy-hungry industries, steel, chemicals, many others, have to move outside of our region. So fusion was the hope for the future. What we observe, there is an international 20 million heavy experiment, and the timelines we get from them is start was planned in 27, now they start in 25, now they start some years later. Basically several iteration loops in promise, something which is able to produce electricity in 2055 plus. So this will be of no use. It's really hard to generate fusion. You basically need ultra high temperatures, something like 150 million degrees centigrade, whatever this means. Hard to imagine. And lot of experiments based on magnets. Attach these, come closer and closer, slowly closer and closer to this limit, but never reach it. Never up to now, it was never possible to really ignite fusion with magnets. But this has been driven by academic research, interested in studying the properties of plasma. And the situation we are facing now completely changed. Helio mentioned it. We have 15 billion private investment in fusion companies. And as a consequence of this, we now see 5,000 heavily engaged, heavily product-driven engineers, physicists, researchers working on the realization of fusion. And this is really the workhorse which is going to make this a reality. It's not the large industry. We will help these startup companies, but it's the startup companies itself who have the science in their hand and who work on this. It's really thing worth to go for. Fusion will be CO2 neutral. There is not the possibility of a nuclear meltdown like in the classical fission reactors. Reason is very simple. It's so hard to realize fusion conditions. So when the power plant makes a failure, it simply stops and fusion stops and nothing further will happen. I already mentioned the geopolitical things. So a little bit technology-wise, I think this will be a little bit more detailed by my colleagues. As an energy company, we see two main leading technical directions. It's not on us to judge who will win my personal gut feeling is both will end up in realizing fusion power plants. Basically, you need these ultra high temperatures. You have two options: put something, a gas, in a donut type form, hold it with ultra strong magnets. Also, you mentioned this magnet development, which is essential for this magnet-based fusion, and just heat like hell to reach these temperatures. And here we see the struggling. Higher temperatures makes the plasma instable. Can we hold the plasma even at the temperatures we need for fusion? But we see significant progress here. Also, Commonwealth fusion, I guess, in 2 or 3 years will be in a position that they ignite fusion in such a machine, which is called tokamak. We, as more industrial people, want to build power plants, so we do more believe in the more modern variant of this fusion reactor, which is called stellarator, because the stellarator is able to work continuously. Tokamak is a nice research engine, will operate for 10-15 minutes, but not continuously. So for industry, only the stellarator is interested. And we have a new kid on the block, developing ultra fast. Very, very simple idea. Use ultra strong lasers and peppercorn and focus all the energy of these lasers in this small peppercorn. And by this energy concentration, you reach the temperatures needed to ignite the fusion. This already has been done by military-driven research in US, the National Ignition Facility. They showed an energy gain, fusion energy to energy in, but this was a machine which was designed mainly for getting data for nuclear weapons, and it's now the task of our startups to show that this can be translated into in an industrial practice. To finish up, why I am here? I think it's the task of the startups to generate heat. Sorry, but for a simplification. But then we are going to take the heat and to build a power plant out of this. So we have very friendly contacts to a lot of startups. And also with Marvel Fusion, we already started in thinking how could such a power plant look like and developed some pre-concepts. So I will take 50 seconds longer to give you also my personal perspective, what the timing might be. We had the public research, which gained a lot of knowledge, which is partly industrially usable. Between 2020 and 2025, we see this huge invest and the formation of startups. Now, as said, today we have 5,000 extremely motivated people working on this topic. I guess we need to wait around 5 additional years to reach 2 main milestones. This is demonstrating that the fusion principle is able to generate sufficient energy to build a power plant out of it, and also to generate the fuel which needs to be generated within the power plant. Also, so it will be no uranium imported from somewhere. It will be very simple, available, abundant materials. With more or less no limit. Then I expected that somewhere in the 30s we will see the first machine, pre-commercial, which generates fusion, generates electricity and feeds this into the net, pre-commercial, and then after 2040 we really expect a rollout of these fusion machines into power plant technologies. And last sentence, do not expect what we need for this. We need to develop a completely new value chain in laser building, in optics, in superconducting magnets, in magnet manufacturing, in all these reactor vessels. So we need to grow certain industries which will create thousands and thousands of additional jobs. And now let's thank you for your attention, and then let's go over to my colleagues to go a little bit more in detail and tell us what we are doing.
Thank you. Well, I think we have time for some questions, if anyone from the audience would like to ask. Yep. Do we have a microphone? Yes, just 1 second.
Thank you. I see 2 layers. One layer is to produce energy through this technique, and the second is the costs for the power plant. You have to have a larger scale to lower the costs, and if you don't have this scale factor, it might be very, very expensive for the first power plants.
Yes.
How do you see this problem, this issue?
Absolutely with you. Fusion on a scale of megawatts or 10 megawatts for me is really science fiction. We believe that these things can be handled at typical power plant sizes of 300 megawatt electrical, which is a good starting point, up to gigawatt. So it will be large ones, and task is really to bring down costs of lasers, costs of components, costs of reactors.
Great, and maybe one more, if anyone has one. If not, I do. I was wondering, where would you rate all of the different countries that are working on this technology? Where does Europe fit in geopolitically with this technology?
We need to see German government spends close to 3 billion, even with some reserve, which is very good. US is spending more private equity. So US definitely is leading in venture capital. China is leading in central investments by the government. But however, for me, it's not only a topic of how much money it's spent, it's a question of the ingenuity of the engineers and also of the supply chain. And for example, in lasers, optics, as well as in superconductivity and magnet building, I think we in Germany and Europe, we are in a very good position.
Great. Thank you so much. A round of applause for Dr. Max. Thank you. Next up, we have Dr. Lucio Milanese from Proxima Fusion. They're one of the leading stellarator startups in Europe working on this technology. Dr. Milanese got his PhD in plasma physics, I believe, from MIT and is a co-founder. So welcome very much.
Thank you very much, and thank you, Max, for the excellent presentation. I agree with pretty much everything you said, and I think it really lays a foundational basis for how we are going to develop and ultimately industrialize the technology. There is a lot of work ahead, a lot of investment ahead, but we have solid foundations, and over the next 15 to 20 years, we're going to build this as possibly one of the largest industries in the history of mankind. And this is perhaps more urgent than ever, at least in Europe. Energy crisis is already again on the headlines, and it's not going to be for the first or the last time. We right now as Europeans spend every year 300 to 500 billion euros on purchasing fossil fuels from abroad. We leave our prosperity and independence to the decision of others, on which we have a dwindling influence. And even more in the age of large-scale computing, access to cheap and abundant energy will be crucial for competitiveness. The good news is that something has been done before about this. in France in fission. So as a response to the energy crisis in the early 1970s, also related to tensions in the Middle East, France made a conscious strategic choice to build fission power plants for its electricity production. And it went over 2 decades from about 5% of the electricity production with fission to almost 80%. And right now, France is the only European country together with, well, the only not because they're also the Nordics, but like one of the major, the only major European country that has actually internationally competitive electricity prices comparing to, for example, Italy, Germany, the UK, Spain, that are not competitive with the US and China. And we expect that something like this could and will happen with fusion in the 2040s and the 2050s once the technology is mature and can be scaled up. It will probably not get to 80% because these days we have renewables that are going to saturate and occupy the space probably until like 60, 70, 75%. But we know that above that at 80, 90%, the costs skyrocket, how much storage you need skyrockets, how much redundancy in terms of photovoltaics and in terms of extra wind power you need skyrockets. So it's just not really feasible to power an industrial economy with 100% renewables. There are also some processes in industries that require high-grade heat that is not easy to generate with renewables. So we are going to see basically fusion coming at a price point and a strategic necessity that will complete the decarbonization process and be the 20-30% base load that right now is occupied, for example, by natural gas. Our solution, our chosen solution, is the Stellarator, as Max also already presented. This is W7X, which is the largest and highest performing Stellarator ever built. It sits not too far from here, actually 2.5 hours northeast in Greifswald on the Baltic Sea. It is a marvel of engineering. It is a complex machine. Some of the aspects actually relate to diagnostics. So a fusion power plant may actually look a little bit simpler in terms of having a fewer ports and some fewer pipes. Though of course there will be other components like blankets and more thorough cooling. But this is our technological and scientific foundation. And today we can hope and work towards bringing this to the market much more effectively because of a number of breakthroughs, including no physics blockers related to theoretical studies that have shown how Stellarator configurations can extrapolate all the way to power plants. The engineering ability of building precision Stellarators, as was demonstrated in W7X, and of course both classical and artificial intelligence computing that allow us to model better and faster and iterate on everything from the plasma physics to the thermodynamics to the structural forces, conductivity, etc. And of course, a key innovation that we at Proxima are also working towards is high-field superconducting magnets. So this is a new technology that allows us to build devices that are smaller and cheaper, and therefore also easier to build. And it's something that is going to be also our first hardware proof point as a company. This is indeed our roadmap, building on top of W7X. Last year, we published the Stellaris concept that was which we had worked in 2024. This is the first fully integrated physics engineering design that is peer-reviewed for a fusion power plant. Next year, we'll deliver the Stellarator model coil as the first large-scale high-temperature superconducting magnet for Stellarators. We will then build Alpha by the early 2030s as the first net energy gain machine that is also able to run in steady state and confines a stable plasma. By the end of the 2030s, we'll be Stellaris, first-of-a-kind fusion power plant, and from the 40s and 50s, we will scale this up commercially to many, many power plants in Europe and beyond. Just to give you a little bit of a sense of how Stellaris compares to other devices like the EU demo and ARC, the magnetic coils are much smaller than ITER, about a factor of a half. And when you consider then the volume, this means that this is basically a tenth, 1/10 of the volume of ITER or demo, and means 1/10 of the cost. And also, of course, the engineering complexity in terms of the weight of the machine and also all decreases. So this is really, really an enabled technology, a transition that is enabled by the magnets. And we are not just in the design phase at Proxima, but now we're fully graduated to hardware and lots of it. You can see a picture of our Munich lab on the left that was assembled this state in, I would say, between 6 and 9 months. And now we keep adding more components and parts and machines to make the cable, etc. You can see assembly one of our coil plate prototypes in the center, and us making, well, actually one of our suppliers making one of the plates and structures for the magnets that I'm going to show you in a second. There's a design on the left of our Stellarator model coil. These are some plates. Actually, there is a ProBeam in the room here who are doing some of the welding with electron beam, which is a cutting-edge technology that was developed in Europe also in support of experiments like ITER and W7X. You can see part of our other halls, cryostats. And here, probably one of the coolest things that we've done so far, these are actually the components that you were seeing being made by a casting in the pictures before. And we're doing this experiment called Mars, this prototyping, to show that we can assemble alpha much faster than W7X. W7X then took 10 years to assemble. We will assemble alpha in 3. And we want not just to state that, but we want to show that this is possible with quantitative measurements of stuff like these coils that weigh about 10 tons, being able to assemble fast and with the right precision. Importantly, we're not alone in this. Europe has a very abundant supply chain in fusion and generally in deep tech. We have built the Alpha Alliance, which now has more than 50 companies from Germany, Italy, France, nearly every major European country. And this alliance together can deliver effectively 80 to 90% of all the components and the value of alpha. And by engaging the suppliers early, we're also able to reduce costs and increase efficiency and speed. We're also supported by world-leading experts in our newly inaugurated industrial advisory board with senior executives from companies like IBM, like E.ON, like Électricité de France, and former investors in leading funds like Breakthrough Energy Ventures. Importantly, and then I wrap up in a couple of minutes, Germany is the right place to do this for us because of the technology, because of the science, because of the talent, but also because of the extreme high level of government support. 2.45 billion investments in fusion announced until 2029 in Germany, 9 billion until 2037. And this is also replicated at state level, where Proxima signed a couple of months ago a memorandum of understanding with the Bavarian government, RWE, the Max Planck IPP, for 400 million of euros investment in Alpha to be built in Garching as a net energy gain demonstrator. And as next step, and as part of this general agreement, we plan to use the former fission power plant of Gunremmingen as a base for our magnet factory and as a base for our first-of-a-kind fusion power plant, Stellaris, which will allow us to move much faster on regulation, on permitting, on licensing, on connection to the grid, and also save a very significant amount of money. And with this, I wrap up, and thank you very much.
Do you have any questions? I'll take the clicker. Any questions for Dr. Milanese? Yes, in the back.
Thank you very much. Thank you very much for your presentation. I have a question about the Alpha device. You say it's a net energy demonstrator. Does that mean that you will have a Q higher than 1, or what will it demonstrate?
Yes, so Q greater than 1 is the target. We're probably going to exceed it by some margin, but this is sort of like our official benchmark. And as you know, probably since you're mentioning the definition of Q greater than 1 is more energy out of the plasma that is put into the plasma.
Thermal energy.
Thermal energy, yes. We're not talking about electricity, net electricity that will be delivered in the first of a kind.
All right, thank you.
Great. Any others? No, I have one. What are you thinking in terms of power generation and where most of this power is going to go? Are you thinking, is it AI data centers? What's kind of top of mind for everyone right now?
Well, sort of like fusion is a solution for all of the above if we can manage, and I think there is a very good chance to bring it to commercial competitiveness with fossil fuels and also with renewables plus storage. For sure, it's a great fit for the AI data centers and the power that is reliable. They need a lot of it, like we're always talking about gigawatts, or if you listen to some old man, even terawatts of power and those sort of things. So it's really a great fit. But of course, like fusion can also be the baseload for the broader grid, so powering household and industry, and importantly also a source of high-grade heat for chemical processes and the steel industry.
Amazing. Thank you. One more? Yeah.
Thank you. What is the biggest bottleneck that you have to achieve this? Because the demand is there, financing apparently is there. Theoretically, you've solved the physics problem. So what is the biggest bottleneck?
Yeah. Well, right now, the biggest bottleneck for us, and what we're working around the clock on, is the magnet. So we have made a promise to deliver this magnet, which is a very complicated piece of technology, by the end of next year. And this will be a very important proof point for Alpha and then eventually Stellars. Of course, there are also like other things that we need to solve in terms of integrated engineering, materials, blankets, but the magnets will be really an enabling component for this next generation of fusion devices, which move away from the massive size of either demo into something that can actually be commercially competitive.
Great. Thank you so much. I think we will have to take questions after. Thank you so much, Dr. Milanese.
Thank you. Thank you so much.
Yeah. And next up, we have Heike Freund. She is the Chief Operating Officer at Marvel Fusion. Her work focuses on operations, industrialization, and strategic partnerships within complex deep tech environments. I don't think I can think of many more complex deep tech environments than fusion power plants. Prior to joining Marvel Fusion, she spent 10 years at McKinsey, most recently as partner advising on global automotive, industrial, and high-tech companies. So please welcome Dr. Heike Freund. Thank you.
Hey, so after we just got a bit of an insight into magnetic fusion technology, I'm going to present to you the other fusion technology, laser-based fusion. As Max has rightly pointed out in his presentation, there are these two big technological streams. But why do we actually need fusion energy? As you're well aware of, humanity always needed more energy. And we are actually only now entering into a new super cycle of increased energy demand if we look into all the announcements that are currently being made around AI, data centers, and so on. One could even mention that for AI might be the first technology that humanity invented for which we don't have the energy source yet, electricity source. So we need fusion energy, and fusion could empower all these great technologies that humanity is inventing. But there's even, besides data centers, a couple of numbers that really got me excited when I looked into the fusion space. I think there's a number out there by the German chemical industry that if you want to decarbonize the chemical industry in Germany, you would need to have 1.3 times of today's electricity consumption of Germany only for the chemical industry. There's other number out there by Lufthansa. If they want to put their whole fleet on sustainable air fuels, they would need half of today's electricity consumption of Germany. So these are huge amount of electricity that we will need in the future for AI, for transportation, for decarbonization of industries. And if we want to keep all these amazing industries that we have in Germany, in Europe, we need additional energy sources. And fusion energy can be the solution to that. We see fusion energy at work every day. If we look up to the sky, the sun is powered by fusion processes. And it's always been a trend of humanity to bring the sun down to Earth and replicate those processes here. Fusion being a CO2-free, safe, and reliable energy source, that would really be the solution to many of the topics I just said, and also increase our geopolitical sovereignty here in Europe. And the amazing news is that fusion has really made tremendous progress over the past 30 years. So if I look into the different technologies, there is a classical magnetic-based technology, tokamaks, there is stellarator technology, there is laser-based fusion technology, and some combinations of in between. And laser-based fusion is the only technology that has demonstrated energy gain in 2022. This is a chart that has been done by the DOE in the US a couple of years back, and it really shows the progress that we have seen along all those technologies, and also highlights that laser-based fusion has demonstrated energy gain. So one could say, hey, amazing, we are done. Energy gain is demonstrated, let's build power plant. But it's not that easy, because like what has been demonstrated in the lab was only energy gain on the capsule, so not wall plug to wall plug. And to get there, we need to have more innovations in technology to really get wall plug to wall plug fusion working in a power plant. And that's exactly what we are working on at Marvel Fusion. So we have developed laser technology in-house that is more than 20 times more efficient than the lasers that have been used at a national ignition facility. It's one of the key pillars to really bring laser fusion into a working power plant, having efficient lasers, compact lasers, lasers with rep rate. We have already secured the funding for those. They are currently under construction, and they will be deployed beginning of next year in a facility that we are building currently in Colorado. But the next pillar is also having an integrated power plant concept. So having not only the pure technologies, but integrating everything holistically into a power plant. And that's something that we are already working on with Siemens Energy, and where we have finalized our pre-conceptual design last year, now working in more detail on the technologies. And then obviously for new technology, you also need political support, because you can do the best you want inside your companies. If you don't have political support for new technology, it will be hard to implement that. But also the political support is now finally at a place at which we want to have it here in Germany. Looking at our roadmap, for us it was super important to first demonstrate our core physics in a very capital efficient way. So we went to existing laser facilities, did more than 2,000 experiments to demonstrate the physics. Then going into proof of technology, so demonstrating a single laser beam, which we can do next year of like our laser technology. Step thereafter will be scaling up the laser energy, then integrating everything into a first of a kind, and then rolling out commercial power plants. Now let's have a look into some of the great work that my team is doing. So here you can see some of our scientists at existing laser experiments. We are running those currently at a facility in Munich, in Garching, and also at a facility in Romania. In Romania, we actually have the most powerful laser facility in Europe currently, and we have conducted more than 2,000 experiments highlighting all the key physics elements. We now also have a proprietary target chamber at the Kala facility in Garching, to which we have 24/7 access and can run even more experiments now, which is super important because we need to gain the data from these experiments to then scale up to the first of a kind installations. And as Max said earlier so nicely, like how a laser is shooting on a peppercorn. So it's not only a peppercorn, otherwise it might be too easy, but a peppercorn in our case exists out of nanostructures, and these nanostructures we are currently producing on wafers, because if we think about industrialization, we need to think about technologies that can actually scale, and wafer production is one of those where we can produce thousands of nanostructures on a single wafer. And last year we've actually been able to produce a world record in aspect ratio, and let me explain to you a bit what does aspect ratio means. In the end, you want to have like very thin pillars in those structures. And if you take a pencil and compare that to the thickness of my hair, you will find out that like my hair is like 1,000 times thinner than a pencil. Now go 1,500 times thinner than a hair, and that is kind of where you are on the thickness of that, but compared to like that thin thing in like 85 meters high. So that's a bit like kind of like what, like if you scale it down and think about the dimensions. So, and that's a world record that we have actually achieved here. I mentioned earlier that we are currently already building our proof of technology facility in a public-private partnership in the US. And I hope that this video is working, because then you will see what just happened over the past year in Colorado. So last year in spring was when we started the construction out there, and within not even a year yet, the building is like kind of the outer shell is already finalized, and our lasers will move. So that building will be finished end of this year, and our lasers can move in beginning of next year. And that will be a key milestone for us to demonstrate our in-house laser technology. I mentioned already earlier that besides developing these individual technology blocks, it's very important to also work on an integrated concept, and that's the integrated power plant concept that we worked on with Siemens Energy, because that really shows you kind of like what are the levers that you need to touch upon when you bring all the technologies together. And I believe here I also have a short video zooming in to, so this is the pre-conceptual design of the power plant, and we're now working on like detailing out more of the blocks, but you basically have two big buildings in which you have the lasers. With the lasers you're shooting into a fusion reactor where the nice peppercorns of that Max mentioned will be injected. You ignite the fuel. The ignited fuel creates particles and heat towards like the outer shell of the fusion reactor, which can then be transferred into electricity. So you have hundreds of laser systems shooting into the fusion reactor. Here you see one of those systems. That is what we are currently building as a first prototype in the facility in the US for a power plant. There will be more technology iterations afterwards, them shooting into the reactor system. I hope that they did a video a bit quicker, but I hope that I still manage in time. So you have the laser shooting into a reactor. Otherwise, I hope that they give me 20 extra seconds. Lasers shooting in, hitting the peppercorn, igniting the fuel, and then moving out to, and then that's actually what Max was saying earlier. The fusion companies have the task to produce heat, and Siemens Energy is then the ideal partner to make electricity out of that. And everything that comes thereafter, and Max, I hope that you're okay with that, is then more or less existing technology that can be used to produce electricity out of the heat we generate. So thanks for your attention. And I'm actually only 5 seconds over time.
Yeah. Do we have any questions? Yeah, at the front.
Thank you. 2 questions. First, there was a very strong statement of becoming the new standard. Does it mean that there are any competitive advantages comparing with magnetic approach? And second question is on the lasers themselves. Do you also plan on producing them or rely on the current manufacturers?
So I'll start with the second one and then come to the first one. So currently we have developed the laser design in-house, but we have then tendered out components to suppliers in the supply chain. So we're not producing the laser class and the diodes ourselves, but we are procuring those components and are then assembling the laser. And now for fusion power plant, we need hundreds of lasers. So there might be topics where we say we need to have a higher level in terms of vertical integration to make that happen. But right now we're procuring the parts, assembling them, and only manufacture some core components in-house. And I think with regards to becoming the standard of electricity production, there's, besides other fusion concepts, there's also renewables and so on. And I believe at the end, you will have a mix of different technology in the electricity mix of the future. I believe in our lifetime, electricity will always be a scarce good. So that's something where you want to have more players, more technologies that can deliver. If magnetic fusion and laser-based fusion both are able to produce electricity at a price point that is attractive for the market is big enough for not only 1 or 2 companies, but also for 10 companies.
Amazing.
One more question. Thanks for a great presentation. I have a question about the fuel. So my understanding is that you need deuterium or tritium to ignite the nuclear process. These are extremely rare material.
Yep.
And that means that if you should be able to run the reactor for a long period of time, you need to manufacture your own fuel. So how far has technology developed here?
It's a very, very important question that you're asking. And I think the fusion-based community is all clear that the tritium that you need for your power plant, you need to produce that on site. Otherwise, you need to have a breeding rate that is greater than 1, and you need to manufacture that in your vessel or on site in your plant. And there is different concepts out there of how you can make that happen. And I think while we do expect that the first of a kind power plants globally will run on DT, there's also options to go to other fuels at a later point in time that would then also eliminate that requirement. Because I agree with you, it's expensive, it will be, it's an additional process that you need to run on site. So getting rid of that ultimately would be ideal.
Great. Thank you so much. Yeah, a round of applause for Dr. Freund. Thank you. Thanks. And next we have Gunter Kraft from Focused Energy. He is the Chief Communications Officer and External Affairs. They're working on laser technology as well, so we'll get multiple views. Thank you.
Thank you for having me here. It's a second laser company in here. And first of all, Max, thank you. Lucio, are you still here? No, he has already left. Thanks for the magnet fusion. And Heike, we are in this together. First of all, before I'm going to start what we're doing, we heard about what fusion is, the energy, yada, 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 all of that stuff. But I think there's one aspect which is really, really important, especially for Germany. And it doesn't matter which one it is magnet or laser. This is a new industry we're creating here. We are creating a new industry. And Max, as you know, we're also working with you together on this, all of it, with Siemens, with Framatome, with Trumpf, and all of the others. This is a major shift in the industry, because in the 2050s, the car industry won't be our biggest industry anymore. And we hope, and we all only can say we hope, this is going to be replacing it. None of us, not Marvel, not Gauss, not Proxima, has ever built, none of the companies, 50 companies out there, has ever built a power plant. We don't know how this works. We think and we hope we know how it works. So we need to be honest to ourselves. That's why we need partners like Siemens, Framatome, and all of the others, because they know how to do it. So this is, I really want to set this in front before I'm going to start. And as you see, we're all working very well together on the startups in here. So let's start. The most important thing, what I liked is here, this came up from our co-founder, Markus Ross. He said, if you take the deuterium tritium fuel, you know, the peppercorns together, and you put it into a size of a can, basically a size of a can, and this is the difference now. It limits the density of the energy. So in the size of a can, in the CDU recently we said until from the time of Jesus' birth, you could have powered your home with this can. That's the density what we're talking about when we're talking about fusion. This is a different age we're going to go into. Fusion has the highest density. The cheapest energy, because you can, if we can make the tritium breeding, you can build it wherever you are. You no supply chains. You don't need these dependencies we have today, this geopolitical, and it's a maximum safety we have in here for this size. This is important when we talk about fusion energy. It's a shift in a new era. So focus energy, of course. We're a laser fusion company. When we based on the principles, nearly on the principles of Livermore, they do it a little bit different. We hope to do it more efficient. We hired a team from Livermore, so the guys who did it, they're working for us now. And we have every day we have the best scientific and engineer. Everybody's saying that. But the more important is, 1.5 years ago, we formed already an industry partnership because we knew we need these people to help us to build that. We're not going to build a power plant. RWE maybe is going to do it, or whoever, and it's ordering, and then Siemens is building it. We just, the little fusion island. We basically just making heat on a very, very efficient way, hopefully. So that's us. So what we do is, in difference to Livermore, Livermore was a laser designed in the 80s, built in the late 80s, early 90s, and they have an efficiency of 0.5%. If we do this, we cannot build a power plant because you have a price of a kilowatt for 50 euro or whatever. It doesn't work. So we need to make the scales, and the industry and the business scales in it. That's why we do the lasers together with Trump and Amplitude. And by the way, do you know that in Germany, we are leading in opto and laser technologies worldwide. So we have the industry already here. Siemens, power plant builder, Framatome, etc. We have them here. So we should use them. So that's what we're doing is we lower the complexity, we build them together. So it's not this big, long laser. We do it in a very, I call it, I'm not a scientist, I'm calling it in the Lego principle. So you can stack them together. And I hope the video is coming. I don't know how to start it from here. So we have a site, we have Beeplis. SRW is an investor in us. And this came because of Beeplis. We transferred the site, Beeplis, from a fission plant in a fusion plant. We already have facilities there, we're building there. And this is how it starts, and we also wanted to show a nice picture. So what we have is, we have sites in the US, we're a German company. We have some R&D over there in Austin because that's where we have the Livermore guys sitting, actually. Then we have Beeplis site. We're building the 3rd facility already there. Yes, the 3rd. And by the way, we already have a spin-off from our technology. So we found out we could do something totally different with it, and we spin it out as a different company. It's also in Beeplis. We have an office in Berlin, and we have when we headquartered in Darmstadt because we is also a spin-off from the Technology University of Darmstadt. So, and by the way, we have a targetry lab. The targets, what Heike is talking about, which we have similar to it. One of our founder is 25 years, did research and development on targetry at the University of Darmstadt. And we made an IP, we get it out. And we have a lab, we built a lab for 25 billion already there. And it's up and running, and we do the target development and all of it. So what's the target? That's one of our propriety. We have the IPs on that. So basically, this is this little peppercorn, what Heike was talking about. And it's a palladium metal shell, polymer in there, tritium and deuterium in there. But what we need to do is, to run a power plant, we need to run it like a diesel engine, 600 times per minute, so 10 times per second. We need to shoot that in and get the 1,000 latest and then make the fusion. So we need a 900,000 per day. So what we do with the target lab, what we're going to do is we do the robotics for it. We do the shape of it, and we do the how this has to be built. You know, we already ready for mass development on it, so this works, and that's really unique IP. And this, by the way, this is the fuel. So basically, this is the new oil behind it. So we have of course, everybody has lasers. We all have the best lasers. We know that, so we develop on it, and yada yada. That's for sure, because all of the companies who are in this field and get funding, they are professional and they have it. So we also do some tests in different labs. We're also building our own lab. Like I said, in Biblis is happening already. Our first laser lab's going to be there. And the Biblis side, it's also going to be an innovation campus for the BMFTR. The BMFTR, the laser hub, is going to be centered in Biblis. There will be also some satellites around it. And I'm done? No. Do I have time? Yeah. So, and it's also, and this is the important thing, and that's why we're working with industrial partner. We don't want to do science. We want to have the industry there, because the industry needs to scale and needs to scale the processes and whatever we need in there. So we will bring the industry there. We have already, like you said, Trump and Amplitude and others are going to be there. This will be an industry platform around the laser fusion in here. It does. We made, by the way, we made a study from fission to fusion. You can download it on our website. ADL did that basically together with RWE, so you can see that. And by the way, in the coming weeks, we make the announcement there's coming up to 200 million private investment just in Biblis to develop the site. Not public, it's a private one. That's it from our side. We all good. We're working together all the time, so the laser fusion guys and the magnet fusion guys, actually, we're a good community.
Thank you so much. Do we have one or two questions from the audience? Yep. Oh, right here. Yeah.
Hi. So with the siting at Biblis and it being a former fission plant, I know that that it's been siting and planned under the fission decommissioning regulatory framework, but it seems like Germany is moving towards treating fusion under the radiation safety framework. Are you worried or do you think that this is a complementary for your siting and licensing efforts, or are you worried it could lead to some dual licensing responsibilities?
Point. Good question. Because working on a fission site, there's an advantage. First of all, there's an advantage because all the regulation is already there. So if you build something from scratch, you need to get a regulation. And you know Germany takes 10 years to get a regulation done. However, as the German government said, we want to have fusion. They yesterday announced a high-tech agenda, and they said, we're going to put the ATG, the Atomschutzgesetz, into the radiation law. They want to do this, I want to start it, I think by you were there, Max, but 2026, they want to have this done. The site itself, it's owned by RWE, and they have to rebuild it. Actually, they should have rebuilt it to the ground, and they said, okay, the money, we don't rebuild it till the end, we rebuild it to what you need for. There are the two domes in Biblis you saw. We needed two domes. In the middle, we built the lasers, and then we have a dome for the target chamber here, and we have a dome for with the target chamber here. Here we run it, and here we make the diagnostics. And so they rebuild it to our needs, and the money they're going to save, they invest in fusion. Yeah. And this is we're talking to them, but it's more or less accepted to do this. And because it's also a business model, and also it's good for you guys from Siemens, because there are other areas where you can sites. Grundremmingen, like Lucio said, they do the same in Grundremmingen. Oh, they do the same in Grundremmingen. So this is actually a business model, how to transfer sites.
Yeah.
You save a lot of money and you speed up. It's about speed because China is coming, US is coming. We will have at least 5 to 7 years advantage of them for the sites.
Right. Very quick question.
Hi, very quick question. In the era of AI, all the industries around the world building complex machines and complex infrastructure, they're transforming. How are you already planning for a 5.0 industry in building this complex infrastructure?
Oh, you mean how we use it, or? Yeah, we use it every day. We're already in AI. We have actually 3 people. They're just helping the scientists and whatever for the AI. There's one advantage we're having is we have the numbers from Livermore. You know, you need data for diagnostic, and we can use that. However, there is all over we're going to use AI. It's full into the company already. It's kind of a DNA already in our company. In each of the engineering development, we do this, and actually that. It was not easy because you have these scientists or engineers who did it for 20 years and they know how to do it. And suddenly you come, hey, there's new technology, use AI. They were a bit reluctant, but after a month, we had a guy, it's called Manolo Perlado. You may know him. He is 75 years, but he ran in Madrid, he ran the whole Institute of Material Science, and he joined us because, I don't know, he likes it. And he said, oh, Gunther, AI is so great. I need to go at the weekend and develop everything on AI. So they're catching up, and this is the nice thing. So it's in our DNA already, the AI.
Amazing. Thank you so much, Gunther. Thank you. Well, thank you to all of our speakers. I think, when I opened this, it was 2 questions. How big could this technology be? How could it impact the rest of the economy? And I think, we got a little bit of a taste of it today, but I think it's a truly transformative technology that is a lot of work, but it sounds like it's definitely worth the prize at the end of it. And then the second question was about why now, and it sounds like a really exciting time for all of these different companies working on it, and sort of a call to action for all of us to help them and come together. So definitely find the companies after this and talk to them about how you can help and get involved. So thank you so much again. Stick around for another session on energy, and I'll hand it over. Thank you so much.